When a central server fails, the entire system built on top of it collapses. The promise of a decentralized network is that it can survive a catastrophic failure by instantly rerouting data through thousands of independent nodes. That resilience is driving massive capital into the space. Projections show the global blockchain market is on track to reach $1.2 trillion by the year 2030. But despite the reputation for being tamper-proof, these systems remain vulnerable. In a single year, attackers drained over $3.8 billion through critical security exploits. Physically, a blockchain consists of a global network of computers, each running software that enforces a set of pre-programmed mathematical rules. To understand why the global financial system is adopting this technology, we have to strip away the hype. We need to deconstruct the physical architecture of the network to see exactly how trust is engineered and how it can be exploited. The atomic unit of this architecture is a single block of data. Every transaction or digital entry is recorded here. A block processes its contents through a cryptographic hash function, compressing data into a unique string called a message digest. Changing a single character instantly scrambles the string. Each block embeds the previous hash. Altering an old transaction shatters the link to all subsequent blocks. This cryptographic interlocking creates what we call immutability. It removes human ledger keepers from the equation and shifts the burden of trust entirely onto verifiable mathematics. Zooming out from the mathematics of a single block, we find the physical hardware maintaining the network globally. These individual computers are called nodes. The ultimate auditors of the network are called full nodes. They download and independently verify the entire history of the blockchain, starting from the very first Genesis block. They check every single transaction against the network's rules, without trusting any outside sources. Archive nodes take this a step further. They act as enterprise-grade databases, requiring terabytes of storage to map every historical state the chain has ever been in, providing critical infrastructure for analytics firms. On the other end of the spectrum are light nodes. Using simplified payment verification, they download only the thin top slivers of data, called block headers. This makes them fast and efficient enough to run on everyday mobile wallets. There is a widespread misconception that all of these nodes are actively building the blockchain. In reality, the vast majority do not create new blocks. They simply act as an army of auditors, enforcing the rules and rejecting invalid data. This varied hardware topology allows anyone from massive server farms to a user with a smartphone to verify their own financial truth without relying on a centralized bank. But with thousands of independent nodes and no central server to make the final call, how do they all agree on exactly which block gets added next? The answer lies in consensus mechanisms. These are the overarching protocol rules that govern how a decentralized network universally accepts a single version of the truth. In a proof-of-work system, specialized nodes called miners compete to propose the next block. They burn immense amounts of energy using raw computational hardware to solve complex cryptographic puzzles faster than anyone else. A proof-of-stake system takes a different approach. Instead of burning energy, validators are chosen to propose blocks through a probabilistic lottery. Their chances of winning are weighted by the amount of capital they have locked or staked directly into the network. Transitioning to a proof-of-stake model drastically reduces the network's energy consumption, while making it economically disastrous for any single validator to attempt an attack. By replacing corporate authority with self-regulating mathematical puzzles and economic game theory, these consensus mechanisms serve as the true engine of trust in the decentralized web. If the math is cryptographically perfect and the nodes reach consensus, how do billions of dollars still get stolen? The answer usually lies in the architectural parameters, or the code itself. One major threat is a 51% attack on the consensus layer. In 2018, attackers compromised the Verge network, resulting in the theft of $1.8 million. In this scenario, a single entity gains control of more than half the network's computational power. This allows them to effectively rewrite the short-term truth of the ledger and double-spend their funds. Attacks also happen at the application layer, targeting bugs written directly into the code of smart contracts. Because a blockchain is immutable, a deployed smart contract cannot be easily paused or patched. Any logical flaw written into the code becomes a permanent, open vector for financial drain. To mitigate this, institutions require formal verification. This is the process of rigorously testing the code with advanced mathematical proofs before any mission-critical application goes live. A decentralized network guarantees survival, but it does not grant immunity from bad logic. The system is only as secure as its consensus distribution and the quality of its code. Even with secure code and robust hardware, blockchain architecture has a strict limitation. By design, these networks are deterministic, isolated environments completely blind to the outside world. This creates what developers call the Oracle problem. Smart contracts cannot natively pull in off-chain data. They cannot see stock prices, weather reports, or verify the fiat reserves sitting in a traditional bank. If you try to solve this by feeding data through a single, centralized source, you instantly reintroduce the exact single point of failure the blockchain was built to eliminate. The solution is decentralized middleware, powered by Oracle Networks. Using the Chainlink runtime environment, a web of independent nodes fetches external data, compares it for accuracy, aggregates it into a single verified data point, and securely passes it through to the blockchain. This architecture enables hybrid smart contracts, making it possible to integrate on-chain logic with the price feeds and settlement requirements of tokenized real-world assets. Resolving the Oracle problem is the critical technical step required for blockchain technology to graduate into a globally integrated financial infrastructure. As the technical architecture matures, the legal infrastructure is actively shifting to accommodate it, paving the way for large-scale institutional adoption. For years, traditional financial institutions were sidelined. Opaque rules and the constant threat of harsh penalties made it too risky to engage with digital assets. That barrier is dissolving. The Securities and Exchange Commission recently issued Staff Accounting Bulletin 122, a pivotal reversal that allows major, regulated banks to custody digital assets without facing punitive balance sheet requirements. At the legislative level, the Genius Act establishes a landmark framework for stablecoins. It strictly standardizes exactly who is allowed to issue them and how their underlying fiat reserve assets must be managed. Following closely is the pending Clarity Act, which defines jurisdictional boundaries over digital commodities, pushing oversight to the CFTC and eliminating remaining market ambiguity. With these frameworks in place, massive non-financial entities are already moving to integrate stablecoins directly into their treasury operations and cross-border payment systems. This coordinated easing of regulatory barriers signals the final phase of institutional de-risking. The network's technical maturity has finally met legal clarity. From a single cryptographic hash, up through a global network of nodes, out to decentralized oracles, and enclosed by standardized legislative frameworks. These layered systems represent a shift in the basis of financial trust, moving from institutional reputation toward cryptographic verification. The convergence of technical maturity and regulatory clarity establishes blockchain as the functional foundation for modern institutional settlement.